This is video help for problem 28.6. Actually, what I'm going to do here is go over the hints that you have, add a few things to them, clarify them, and actually correct some of their equation numbers that you see there, because that was for an earlier version of this chapter. The whole point of this stuff here is we're including the noise now from what we had before. And like before, when you're looking for, an extremum, you are actually can show and convince yourself that if I'm looking for, when this thing is an extremum as a function of m hat dagger, think of m hat dagger as independent of m hat. I'll explain in a second why. And you can just take this derivative just as if this was just a single good old functional, just function of one variable, one real variable even, that we did when we first learned calculus. Just take this derivative and you just get minus beta dagger times the rest of this stuff here. Minus beta dagger times the rest of that stuff equals 0. Now, let me just explain something. If you went out and carefully looked at every matrix element here and took the derivatives with respect to that, you could show that that result can be rewritten in terms of a matrix equation, which is exactly this thing. The other thing is to think of m hat dagger can be considered independent of m hat because they have a real and imaginary part. And so you can think about the real and imaginary parts as independent, or m hat dagger and m hat as the independents. Finally, in this initial discussion, 28.36 really should be 28.40. I rearranged this to look like this. Now, this is a square. This whole thing is a square matrix, so I can invert it. See, here it is, inverted, and solve for m hat by multiplying through by that inversion. So now I've got m hat. That's the master formula that we have. That's the generalization from what we had before pertaining to, the first problem 28.2, and that, early part of the chapter, except now we've got the noise coupling, the possible noise contributions in our signal. This, by the way, this equation can also then be used to relate the noise in our alias signal as it translates then into the noise associated with our reconstructed spin distribution or magnetization. Here's some equation number changes. I'm going to Xerox this up, scan it, that is, and send it to you so you'll have all these numbers correct. Now for this last calculation. It's just, kind of tedious to write it all out, but it's straightforward. I think you'll find it easy. We're interested in the chi-square, the variation, the standard deviation squared associated with m. That's the error then, a to m dagger. But then you relate that to eta through this equation. So now I have just putting in here. By the way, remember daggers. When you take the Hermitian adjoint of AB dagger, it's B dagger, A dagger that get reversed. And the same thing will happen as we're going through some of this calculation. And now, so I'm just plugging in. And the thing is to realize that this average just refers to the average over this error, this random error in eta in S hat. I should probably put hats on these things. And this thing here just gets, that's definition of our noise matrix. I stick that in here, and if I just stare at this thing, I can see that I can rewrite this. And remember the basic thing, A, B, total dagger equals B dagger, A dagger. I can just rearrange this so that it's just this guy inverse times itself. And that's 1. And you'll just see, just being careful of the ordering and the Hermitian adjoint identity. And you contract, it just collapses down to just this. This is 28.45. Now, in part B, we're going back and looking at coils now, and we're looking at two, coaxial coils opposing each other. And that's just a freshman calculation when you're trying to ask, what is the magnetic field due to this, in the reciprocity, at the two spins we're looking at. We're looking at a spin at the distance 15 from this thing and 25, those points P and Q in the problem. You can just look at the B field, how it drops off, look at the ratio at 25 to 15 and get that number shown in the problem. And moreover, this problem fits perfectly back into 28.21, the stuff pertaining to our first homework problem in this chapter. And the A and the B are left coil. See, the left coil sees a strong A, A bigger than B, remember. B is 0.3, A is 1. For the spin 1, and whereas the right coil sees spin 2 is having the bigger signal, or in reciprocity, making a bigger field there. And by symmetry, then we just have AB, BA. It fits right into 28.21, and you can just take those formulas to finish calculating, out your G factor. Finally, in part C, never mind a numerical calculation. We shouldn't have said it that way. If you are uncoupled, you can see that sigma squared cancels out exactly. If you look at the, the formula, back on this page, if you look at this formula, this psi inverse, this -1, -1, and this psi inverse, then this -1 kind of cancels the effect of this. And so these two guys just cancel out if they were just simply some factor. If this was just proportional to some sigma squared, diagonal, then it would just cancel this sigma squared because it's inverted. So that's just trivial. Finally, for the last part of the question, just think about the mutual flux between these things. Remember that we're interested in what's the flux due to this coil, picked up by this coil, because that's the question about whether this guy picks up this guy's noise and vice versa. Here, with these guys a bit of a distance apart, compare that to when you've got two coils here, coplanar, lying close by, and ask yourself, which one has the bigger coupling.